In this example, we are going to be designing a vibration isolator for a rotating piece of machinery. So we're given the properties of the rotating machine, its mass. It has this eccentric mass that's rotating around that central axis, and specifically it's going to be rotating at 10 hertz. So our job is we get to decide what the spring constant is and what the damping coefficient is for the isolator. But we have some conditions that we need to adhere to. So for one reason or another, the damping ratio has to be 0.2 for the vibration isolator. This is going to ensure we have an underdamped system like we've been working with. And as part of the job of the vibration isolator, we want only 10% of the excitation force to be transmitted into the foundation or into the floor. So again, this thing is rotating, it's generating a vertical force. We're ignoring the horizontal part, but it's generating this vertical force, and we want to have only a small portion of that, 10% exactly for this example, to go into the foundation, and then that could be transmitted to other machines around it. We're going to do this analytically and then verify it in simulation. So how this differs from the previous examples we looked at and why our methodology is going to be a little bit different is we don't know ahead of time what K and B are, and in the previous examples we did. What this means is going into the solution steps, we're not going to know what the natural frequency is, and that is going to necessitate the use of the relative frequency Bode diagram as previously described. So as always with these mechanical systems, we want to start with our free body diagram. So on the left side, I have the free body diagram of the actual machine. So we see it has this rotating force, like we saw in the previous example, the mr omega squared sine omega t. Really all that matters is that it is a sinusoidal input, as we're going to see in a moment by labeling it here. And then we have the force of the spring and the force of the damper acting on our machine as well. The way I've defined x, for the spring and the damper to be in tension, it'll be a negative kx and a negative bx dot. And then we have the inertia of the machine. So again, notice my use of big M here is the mass of the whole machine that is going to be vibrating up and down. Little m is just the eccentric mass. And we want to keep in mind here, we're going to be looking at transmissibility. We care about the output force into the floor versus the input force from the rotating machine. So it's a little bit different than what we were looking at before, where we might be looking at the displacement versus the force. And we'll see how this ties into the transfer function we're creating to get transmissibility. But since we want to know the force that's being put into the floor, we also need, on the right-hand side here, I have a picture of the floor. So we see that it has the equal and opposite forces from the spring and the damper, and then the force from the floor is going back up, is that F of t. And since the floor is not going to be moving or not accelerating, or we're going to say it's very small, the right-hand side is going to be 0. So really what we're looking for is that Ft. What is that kind of returning force? That's the total force that's going into the floor there. So from the right-hand picture, I'll skip a couple of the steps here. But after we do a Laplace transform and we do that equation of motion, we get the force in the floor. We get the relationship between F and X from this free body diagram is K plus Bs times X. And then we can put it together. Because again, the transfer function we're actually looking for is the output force, that going into the floor, versus the input force from the rotating machine. So the transfer function we desire is this F over P as described here. So briefly looking at the Mathematica, just so we can see where the algebra is coming from, I have my first equation is from that left free body diagram, and equation 2 is from the right hand one. Putting it together and solving for F as our output, we see that F is this expression, and we can divide through by P to get the desired transfer function, and that's what's written on the slide. So we have the Bs plus K over Ms squared plus Bs plus K, and right away I'm going to put this into the standard form we're used to. So I'm dividing through by big M here, and I get the rightmost equation, where now I have a coefficient of 1 in front of my s squared term. I have my B over ms plus K over m. And then the numerator, I have to also divide everything by m there, so I'm doing the same thing to the top and the bottom. And note on my right-hand picture, I'm assuming that Ft is positive up. I could have made the opposite assumption. That would have been okay. It won't change really much in the analysis. Okay, so what do we do with this transfer function? M was given to us in the problem. That was the mass of the machine. But what we don't have is the K and the B. We are supposed to be designing that for this vibration isolator. So I can rewrite the denominator now that we are in the standard form with a coefficient of 1 in front of the s squared. So I know that it should look like this, 2 zeta omega n s plus omega n squared. And then if I look at the top, the numerator, I have a b over m there, so I know that should also be 2 zeta omega n, and I have another k over m, so that should also be omega n squared. So in this case, because that the coefficient of the s and the constant match, I can just make sure that I write them the same. But really I'm looking at the denominator first and looking at that standard form. And now I can apply a little bit more knowledge about what I know. Is that here I am given that the zeta has to be 0.2, the damping ratio is 0.2, so I can put that value in for zeta. So now I have this expression. Now I don't have enough information to know the natural frequency. Again, we're going to be finding what that is because we're going to be setting the spring constant, but right now I don't know what it is. So I can't at this time take my g of s expression and put it in to make a Bode diagram because I have this variable in it, omega n. So this is the step where we know that we probably need to use a relative frequency Bode diagram. We can't go down the same path we did in the first two examples. So this is the kind of that splitting point where we're going to solve this a little bit differently. So as I mentioned before, to make the relative frequency Bode diagram, what we can do is take this g of s, and I'm going to make a new transfer function I'll call g prime. So it is not the same. This is a different transfer function that we're going to be plotting. Because what I did is I'm setting my natural frequency to 1 in g of s, and that's how I'm getting this g prime of s. So we see now I have 0.4s plus 1. Omega n was just set to 1, and just made a quick fix to the denominator is s squared plus 0.4s plus 1. So now this g prime is something that we can put into MATLAB and make our Bode diagram. But before I make the Bode diagram, what are we actually looking for? Why do we need the Bode diagram? Well, back in the problem statement, we were told that the transmissibility should be 10%. We want only 10% of the input force to be transmitted into the floor. So what does that actually translate to? Right, so that TR is 10%, which is also expressed as 0.1. So that is the linear ratio really that we're looking for. But in the Bode diagrams, our magnitude is by default going to be expressed in decibels. So I do want to make a conversion here to see what is 10% or 0.1 in decibels. So my quick conversion here, I went 20 times the 10 log of that 0.1 is a negative 20 decibels. So that is, once we make the Bode diagram, what we're going to be looking at. So we can look in the MATLAB now. And what I have going on here is I'm going to first designate what my transfer function is. I'm going to do that in 116. So I'm doing this a little bit more generally. So remember from the transfer function, the g prime is what this RF is in line 116. This is going to be, again, not my original transfer function, but the one I use for the normalized frequency where I set that omega n equal to 1. So I'm assigning its numerator and its denominator. Let me just run that section. So we see that RF is exactly what we had on the slide for g prime. And I'm going to make the Bode diagram of this function. And just for display purposes, I am going to start with omega values from negative 10 to the negative 1 to 10 squared, or 100. So I'm using a log space here to do it. We'll see how that's reflected in the Bode diagram. And I'm doing this in a little bit more customized way like I did in the previous example. So on 120, I'm using Bode to get out the magnitude values and the phase values. And then I'm going to plot them myself. Because one, this is a relative frequency Bode diagram. I want to remember that when I'm looking at the plot. So as I saw before, I'm going to make the top subplot my magnitude. Out of Bode, when I save the data, into big M, that comes out in linear. I am going to plot it in decibels just so it looks like all the other Bode diagrams that we've been working with. So I'm using the semi-log x for my frequency, although that's really normalized frequency as we're going to see, versus my magnitude in decibels. And this is, because the way I set my transfer function is a transmissibility, is an output force over an input force. And then in the second subplot, the bottom one, I'm just going to show my phase. And again, that is going to come out in degrees. For this example, we're going to see that we don't really use it, but I'm still going to create it. So let me just run this section here. We see again that x-axis label is omega over omega n, is the ratio of the input frequency to my natural frequency. So these values here, this 10 to the negative 1, 10 to the 0, 10 to the 1, are ratios. They are not the input frequency in radians per second like we've seen before. The top, I'm seeing my transmissibility. That is just magnitude. It's, again, that output force over my input force ratio, and that's in decibels. And then the bottom is my phase. So if I look at the top diagram, the magnitude, if I go here, let's say my input frequency is my natural frequency. That means that their fraction is just 1. That's 10 to the 0. Notice that the peak of the transmissibility is not at 1. So the peak is not occurring when I'm driving it at its natural frequency. And that makes sense because, again, the peak occurs at the resonant frequency. So I don't know what my natural frequency is yet. I'm going to be figuring that out. But if I find that square root of 1 minus 2 times zeta squared, I find that that is 0.9592, so about 96%. So the resonant frequency is about 4% lower than my natural frequency, and that's why I see this left shift of the peak that's a little bit to the left of 1. All right, but really what we're looking for in this one is, again, back to the prompt, we wanted a transmissibility of 10% or 0.1. We converted that already into decibels, and we saw that that was negative 20 decibels. So let's see what we have here. So if I mark my plot here at negative 20 decibels, that gives me an x value of 4.719. I can also find on the phase diagram what 4.719 is going to look like. Again, it doesn't really impact our solution here, but I can find its value. About negative 113 degrees. But more importantly is the transmissibility. So what this is telling me is that if the ratio of my input frequency to my natural frequency is 4.719, then my transmissibility is going to be negative 20 decibels. As that ratio increases, we see the trend here is that the transmissibility is going to continue to go down. And if relative to this point, my input frequency is lower, if that ratio gets smaller, if I move to the left, my transmissibility increases. Here I'm looking specifically for exactly that 10%. So this tells me that in my design, my ratio of my driving frequency to natural frequency should be 4.719. All right, so let's go back to work some equations now. All right, so this has to be true. The ratio of driving to natural is 4.719. I am given in this problem my driving frequency is 10 hertz. Our standard unit, though, is going to be radians per second, so I need to convert my 10 hertz by multiplying by 2 pi to get in 20 pi radians per second. So now the only thing I don't know is the natural frequency. But I have one equation, one unknown. I can solve for the natural frequency is going to be 13.3 radians per second. That will guarantee me that I have this ratio of 4.719, which again, going back to the Bode diagram, gives me a transmissibility of 10% or negative 20 decibels. Now, how can I use this? Well, remember I had my transfer function put into that standard form, and I know that my constant term, that k over m, is going to be omega, my natural frequency squared, omega n squared. So it has to be true that k over m equals 13.3 squared. Well, m was given to us, the mass of the system was 100 kilograms, so the only thing I don't know then is what the spring constant is. Keeping 3 significant digits, the spring constant has to be 17,700 newtons per meter, or 17.7 kilonewtons per meter. So if that is my k, with my given m, that will give me my natural frequency of 13.3 radians per second. So this step has now given us what our k value should be to get that 10% transmissibility. We have our k figured out. Now we can move on and look at what the value of b should be. What should our damping coefficient be? Well, again, looking back at our original transfer function, this is not the normalized one. I didn't set omega n equal to 1. This is the original g of s. We know that here, that s term is 2 zeta omega n. So 2 is a constant, zeta was given to us as 0.2. We know from the previous step that our omega n is 13.3. M was provided, so the only thing we don't know is b. So solving this equation, keeping 3 digits, our damping coefficient should be 532 Newton seconds per meter. So that will guarantee that we have that 0.2 as zeta. That will guarantee that we have the correct natural frequency. So we have our k, we have our b. Now what we can do is make sure that our analysis gives us the correct results, and we'll do that through simulation. Up until this point, all I've seen is I'm using this P, this capital P here, but now I can put in some specifics. So back to this P of t, I know the eccentric mass, I know the driving frequency, that 10 hertz or that 20 pi radians per second. I know the radius, that eccentricity is 0.5, and I can fill in all the details there. So the actual input force is going to be 395 sine 20 pi t. Really important here is going to be that the amplitude is 395. So if we were desiring, by designing this vibration isolator, that the output was only 10% of the input, that means that that output force in time domain should be 10% of the amplitude. So instead of 395, it should be 39.5. And we should see it has the same frequency and then maybe some phase lag introduced as well. So if this is true, our design has worked correctly. We're getting only 10% of the input force as output force. So let's verify this using Simulink. Right, so let's take a look at our Simulink model. We have an input, that P of t, going into our transfer function, and it comes out as Ft, the force transmitted into the floor. So take a quick step back. Now that I know B, now that I know K, I can assemble my G of S here. I also know M. So I know what all of these coefficients should be as numbers. So if I go back into Simulink and open this up, I can put in all of those proper numbers and see what the results are. Right, so I have my numerator and I have my denominator. This is actually going back to, I have m, s squared, bs, and k. So this is before I divide through by m. I could use either version. It's the exact same transfer function, but this is all the way back to my original version of it. Okay, so that's the transfer function. Let's see what the input looks like. It's a sine wave of amplitude 395, which we just figured out. That's that mr omega squared. And its frequency is 20 pi, or I just put it longhand here of 10 times 2 times pi. And that is going to be our input. So that goes into our transfer function, comes out as ft. That goes into this vector concatenation, which is then going to go into MATLAB, and we can see what the results are. Right, so in this sim out, we're going to see the input function p and the output function ft after the simulation. Right, so this little piece of code, I'm going to run the simulation. Going back here, I'm going to just run it for 2 seconds so that I can see some of the detail that's going to come out of it. Right, so let's run this. And quickly, if we look at what the code is doing, I'm running the simulation as I've done before. When I run that sim, I get this sim out struct, as we saw. So the first column of it is going to be the top piece of my Simulink, that's the P, and the second column is going to be FT, because again, the columns are in the same order vertically as this vector concatenate is. So the top plot, I'm going to be plotting my input, and the bottom is my output. So the top is the P of t, and the bottom is my FT. So going back to here, making it a little bit bigger. All right, so the input is stable. That's just that 395 sine function, so it just keeps repeating itself. If we look right now at the output, for the first, let's say, 1.5 seconds, it's kind of moving all around here. It's oscillating, but kind of at these multiple frequencies. By the time we get to about 1.5 seconds, now we see that the output has leveled out, and it's this sine function that we expect it to be. Remember, when we're using the Bode diagram, all of our analysis in this course is based on the steady state response of our system. And so far, I've really just cut out what we call the transient phase, the stuff before it settles into this repeating sine pattern. So the first about 1.5 seconds of our output is in the transient phase. We're not looking at trying to model that. We're not trying to find the equation that determines that. After 1.5 seconds, now it's this steady sine wave. So let's just look at the values we're getting. So if we look at our input, I'm picking out a peak here. We have a Y value of 395, and that's by design. We say it has an amplitude of 395, but really what we want to check is, does the K and the B that we selected do what it was supposed to? Make the output only 10% of the input. So our input's 395. Let's pick a peak here as best we can, and we're getting out a Y value, a maximum Y value here. We're seeing about 38.66. So it's a tiny bit lower than we expected, but there was some rounding from the K value and the B value I put in, because the K value was only 3 digits of significance, and the B as well. So it's a little bit off, but it is approximately 10% of the value of the input. So as a quick recap of what we did here, we used the relative frequency Bode diagram because we did not know in this design step up front what the natural frequency was. So we couldn't just put in the Bode diagram. We didn't have enough information yet. So by setting that natural frequency to 1, we were able to make a relative frequency Bode diagram and at least see what's the relationship between the input frequency and the natural frequency. From there, since we had the desired transmissibility of 10%, then we were able to select what the natural frequency had to be in order to get that 10%. Now that we knew the natural frequency, we could get the K, we could get the B from our transfer function. So on paper, it looked like we did what we were supposed to. So then we verified it in simulation using Simulink. And we see here that if we see what that F of t is, the force that's being transmitted into the floor, that once we get to steady state, indeed, we are at about 10% of our input amplitude as our output amplitude. However, we do have that transient response first happening, and we do see actually the amplitude there is significantly greater than the 10%. So it's not until 1.5 seconds we settle into the steady state values, and then our assessment is correct. The K and the B we selected are providing only 10% of the output amplitude of the input amplitude.